Good morning. This is lecture 42 of our course on analog electronics. And in today's class, we'll look at how one can move from the circuit that we had to the CMOS inverter. And we'll understand how the CMOS inverter can indeed actually be used both for digital applications and for analog applications. Okay. So, in the previous class, we had looked at one particular circuit, right? And then I said that we had looked at a circuit which was basically a common source amplifier, a PMOS common source amplifier, which had an NMOS transistor as its active load, correct? So, in today's class, we'll start by drawing the incremental circuit for that particular full circuit that we had, and we'll look at what the gain is, and we'll proceed from there. Okay. So, the circuit we had was something like that. I had this was a PMOS transistor operating off VDD, and I had an NMOS transistor which was my load, correct? And in order to bias that NMOS transistor, I had used a current source biasing. You can use any kind of biasing, there is no real issue. I just used the current source biasing, and there was that thing which connects that to that. And then what else had we done? I said my output was taken here, correct? And then for the input, you have to do something. What I had done was to use a drain feedback biasing with a large value of feedback resistance. You can calculate what that large resistor should be and all of that the regular way. And we had also fed in the input here. Okay, is this a circuit we had? Did I miss anything? Just look back and see. It's the same? Okay. One can have another version of the same circuit just for fun. Okay. I want to, instead of using drain feedback biasing, say I want to use a current source biasing for this transistor M1. Correct? So, what can I do? I'll have this transistor as it is. Similarly, that transistor as it is. Okay. And I'll just draw it slightly longer so that I can fit in what I want. And there's a current source. We haven't yet discussed how to make a current source. I'll give that in your exam, and I'll motivate how to do it, so it will be straightforward. Okay. And then I want to use a current source to bias this transistor also. So, what can I do? We have done some things like this earlier. I can put another transistor here, right, and connect its gate to this line, right, and then go upward and connect a PMOS transistor this way here, correct? And what should I do further? I am trying to make a current source. Sorry, I am trying to make a current mirror. So, for this PMOS, I can connect its drain and gate. Okay, so that will set this value of source to gate voltage, and then I can use this guy to connect to this, right? That will be my biasing circuit. And if I want to feed in my input, you remember that we had discussed that you need to actually put a very large some resistance here, some base resistance, okay, and we had discussed why we need that and all of that, right? Why did we need it? Yeah, well, everything is for large gain. Any other ideas? You remember? We had this in the quiz also. Yeah, right, because the source has some internal resistance. You want the resistance that the source sees to be much larger than the source resistance. That's why you had this RB. It does not affect your biasing circuit. Okay, and then similarly you can have the output, and this is okay. So, this is a PMOS common source amplifier with active load. Only difference is M1 biased using drain feedback, And what about this other one? Using current. Okay, so just two versions of it. You can have any kind of circuit. You know how to analyze all of these circuits actually. Okay, so what we'll do today is that we'll start with just taking the first one, right? So that is good enough for us, and we'll move with this first circuit. And to make things much simpler also, I want you to draw the incremental circuit of this guy. To make things simpler, I'll just take the limit of R large being infinity. You don't need it to be infinite, but let's assume R large is infinite, and then you do draw the incremental circuit. Okay. How do you draw the incremental circuit for this guy? All of you try. Alright, so we can name the transistors. Let me call them M1, M2 and M3, and then let's proceed. So first start with M1. What does M1 see? Okay, let's also name the terminals. That is the source, that is the gate, that is the drain. This is again drain, gate, source, gate, drain. Right? So let's now go back to M1. It's a PMOS device, right? And what happens to its source? The source is incrementally grounded, right? So let me have one ground line here. So the source is incrementally grounded. And what about the drain? The drain, okay, we don't know what about it. So let's only take this guy. So it is going to have its R. It's a PMOS device, so I'll call that as RP. This is basically the channel length modulation resistance corresponding to the PMOS device. Okay. So and then what about its input? So if I call this as Vi, where does that input come? That's something, and that is your Vi. All right. Thus is so far no problem, right? Okay. This is your transistor, and this is GMP times Vi. Okay. Now draw the bottom transistor M2. How does that operate? Again, I have something here. So let me call this terminal as X. Okay, that point let me call as X, and so this transistor again has nothing fancy. Okay, what happens to its source? Its source is also incrementally grounded, and this M2 will have a resistance. Let me call that Rn, and this is going to be GMN times Vx. Correct? You don't know what Vx is. We'll come and sort that out. All right. Now, what's the next transistor we have to draw? We have to draw M3. Okay. So let me just shorten this out here, and there is some voltage here. Call that as Vx. All right. Now, how about M3? M3 is another transistor like this. Okay. And I am saying that M3 and M2 have the same gain. So I am going to call this as GMN times, what is the voltage? Again Vx, right? Again Vx. All right. And then what else does this guy have? The current source becomes an open. Very good. And this drain gate short will come from the, so this is drain and this is source. Okay. So this Vx has to get connected all the way up to there. Okay. And what else should be there? You have some resistance. Let me call that as, okay, I am assuming that M2 and M3 are identical. So, I will have some Rn here. Okay. Is that all, or have I missed any other connection? Yes, between transistor M2 and M1. So, this is transistor M1, this is transistor M2, this is transistor M3. So, I need to have one more connection which connects my drain of M1 to drain of M2. So, the drain of M1 is here, correct? Drain of M2 is here. So, there is one connection like that. Is that right? And where is my output? Output is basically at that break. That is my V out. Correct? All right. Now, can you help me simplify the circuit? Okay. Look at M3 first. Okay, because we have to figure out what this Vx is and all of that. Look at M3 and look at the argument. All right. Now, what is the current flowing here? What's the current flowing in this? 0, right? Because this is open. So, the current here is 0. If current here is 0, what do you think Vx is? Look carefully. This is 0, okay, which means that this current plus that current must be equal to 0. All right. Find one solution and see if that actually works. Look at the value of Vx equal to 0. Check if Vx equal to 0 is a consistent solution. Because if Vx equal to 0, what is this current? 0. Vx is 0, which means this current is 0. 0 and 0 add up to 0. So, Vx equal to 0 is actually is a consistent solution for this circuit M3. All right. All right. If Vx equal to 0, what can you do about this guy? What happens to this GMVx? This thing also becomes 0. So, I can remove that one. All right. Now, can you simplify my circuit? Yes. Okay, good question. Okay. So, look again, all right. Let me remove the stuff which I had drawn. All right. I don't know what the value of Vx is, but I know one thing. I know that this current is 0. Why? Because this is an open here. So, if this current is 0, now this current is splitting into two arms. One is that and another is this. So, this one plus this one must be equal to 0. All right. Now, you can actually solve Kirchhoff's voltage law and get the value also, right. What does this mean? What is this current? GMVx, and so GMVx into Rn, correct. All this current has to flow through this Rn. So, you can say that GMVx is the current into Rn must be equal to what? Or rather, I am going this way, right. So, minus GMVx Rn is equal to Vx. How is this possible? Only if Vx equal to 0. So, you can apply Kirchhoff's voltage law and current law and also get it, but I just said, okay, if Vx is 0, is it consistent? It appears consistent, so that is also a solution. Okay, very good. Now, you have this. Can you okay, if Vx is 0, this M2's current source also is effectively 0. All right. So, now can you simplify this circuit? Very good. Okay. So, I can actually draw it in this corner here, though it will not look very nice, but I think everyone will understand it. Okay. So, the simplified version of the circuit will be what? I will have my Vi, correct, and then that goes to source, that goes to 0. I have my current source corresponding to the top transistor. So, it's GMP times Vi, and then I have an Rp, and then this Rn effectively comes in parallel with my Rp, correct, and I have my V out here. So, even though the circuit itself looks complicated, the moment you put it down, the final equivalent circuit is very, very straightforward. So, what is the gain of this transistor? This circuit minus GM times GMP times Rp parallel Rn, and that is what we saw, right. Yesterday I said that if so, what is the slope of this guy? So, just to remember, This red line was for coming from which transistor? M2. So the slope of this guy was 1 by R N. The slope of this guy was, okay, let me put it in red, and the slope of this was 1 by R P, right, in the saturation region. And obviously if both R P and R N were infinity, then these two will become flat, so you will get extremely high gain, correct. It's like you had a load resistance of infinite resistance, and the idea of having the active load is that even with a low value of the supply voltage, you can get extremely high gain. Alright. Okay. Now this is our small signal circuit, and we did this when R large was infinity. If it were not infinity, you can keep it there, and then you want to get this final answer, you will have to ensure that this R large is large compared to some other components in your circuit, so that the gain effectively appears like this one, that all of you have done, so I am not doing. Okay. So this is small signal analysis. All right. Next, something which we have not done for many of these circuits, which is the large signal analysis. And just for thing, I will keep this circuit with me. Okay. Now, in order to do the large signal analysis, I am going to do something slightly fishy. So, just look what I am up to. Okay. Now, in this particular circuit, right, the bias is such that how does the transistor M1 get biased? Because you have some current flowing here, right. So, this current is some I1, that current is flowing through this M3. Because of that, it sets up a VGS voltage here, that VGS biases M2, correct. That current is flowing in here, and then you have a drain feedback, and that sets up what the gate voltage should be, and then this M1 gets biased. Okay. So, in this way, the value, the range about which VG can move is actually very large, very small, right, because of the fact that there is this feedback loop working and all of that. But I want to look at something little more general. So, what I am going to do is actually to remove all of this, okay, and then I am just for fun, let me say I am going to put just a voltage here, let me call that V capital G. So, that is the total voltage at the input. Similarly, this one let me call as the total voltage V phi, or because now it is anyway the drain, I can call this as V D. Okay. So, by putting it like this, assume that you can change this VG over a very large range. Maybe you just have a voltage source there, you do not want any feedback for that one right now, you just want to look at what happens if I sweep my VG over an extremely large range. Okay. And because the moment I draw it, it will become clear as to what I am trying to do. All of you have seen this kind of thing before. Okay. So, my input is V capital G, that is the total input, okay, and my output is V capital D, again my total output. I want to make a plot of this. Is that okay? Everyone's clear as to what I am trying to do? Okay. Now, in order to do this, we should have some figures, otherwise everyone will get confused. So, let us draw something first. Okay. Now, there is this I1 flowing, right, and through this M2 was your NMOS transistor. So, let us assume that M2 is biased. Okay. And for fun, what I will say is that M2 has a value of its output resistance to be infinite, just for fun. Okay. I will not have M1 to have that kind of thing. I do not want to have both as infinite, neither do I want both to have a finite value, because drawing both those cases is a little more involved. I will make one of them infinite, so it becomes flat, other one I will give it a slight slope, so it is easy to draw, but you can always work out the details later. This is to just get an idea of what's happened. Okay. So this is the characteristic for what? What am I plotting here? I. And what am I plotting here? So this is ID and this is VD. Okay. And this is for which M2. Okay. Now I want 2 copies of this, so I am just going to keep a copy of this. Yeah. All right. Now what is the value of this current? The way it is drawn, what is the value of this current? There is only one current I have drawn in the circuit, I1. Right? It should be, right? Because I have I1 here flowing through this and then through M2, so it should be I1. Okay. Now, let me say I take Vg to be 0. Okay. Let me take Vg to be 0. So before that, possibly I can draw one characteristic of this Vg when this thing was actually working like an amplifier. So when it's working like an amplifier, what did we say? How should this other characteristic look like? If I say this was VDD, the M2 characteristic, how did we want? We wanted both to be in the saturation region, right? Only then it works as an amplifier. So, and then as I said, I am going to have some value of the resistance there so that it's easy for me to draw. Something like that, and then let me say I have a little bit of a slope, so it goes. Okay, this is obviously drawn very exaggerated, but I want to draw it like that because it's easier for me to draw it. Okay, so this is your M1, and let me say that this particular one corresponds to some Vg star. Okay, so in this particular configuration, this thing works as an amplifier, right? You sure? Okay. Now let me say I take Vg equal to 0. If I take Vg equal to 0, right, where do you think this particular M1 line will appear? Will it go up or will it come down? Why? Right? Because what you actually want is the source to gate voltage. So if you reduce your Vg, your source to gate voltage for the PMOS device, M1 is the PMOS device, the source to gate voltage will actually increase. So what will appear? What will happen? The current should go up. So you can think of one value of Vg for which, or other, you can assume, you can possibly think that you will have a thing like this, and this is again your VDD. Is that right? So basically what you are drawing is, there is a parabola from here, right? There is a parabola like that, right? So that same parabola exists here also. Is that right? So okay, the way I have drawn it is not correct. So we can remove this. Just clean it up. You come up to there, and then you will have that slope, something like that. Is that right? Okay. Now for this particular value, so this is my Vg being equal to 0. Okay. What is my output voltage? From this graph, how do you find out what the output voltage is? Where is that intersection? No, look carefully. What have I drawn the characteristics of? This is the characteristic of the upper transistor M1, this is the characteristic of the lower transistor M2. Same current has to flow through both, correct? So you find out where is the same current flowing through both? Only at that point of intersection. And what is the voltage that will appear? Vd, the voltage corresponding to that current. So this will be your, that will be your output, right? That will be your output when, so I'll just say that is my output. So what can you say about this output? So if I were to plot my VDD here, Okay, and correspondingly I'll plot my VDD there. Does it look equal? Yeah, I think it's okay. Okay, so what can you say about this output voltage? Will it be close to VDD? Yes, right? The way you have drawn it, it looks obvious. Will it be equal to VDD? Never, right? So it will always be slightly less than VDD. Okay, very good. Then what happens? As you now slowly increase your gate voltage, what will happen? Right? So if you increase your gate voltage, what will happen? There's going to be some region wherein it's still going to be in the, so in this particular region your M1 is biased in what? For this particular characteristic, M1 is biased in triode, right? M1 is in triode, M2 is in saturation. So there is going to be some region, right, as you decrease your gate voltage, where M1 is going to still remain in triode. So that you can draw here, right? How will that look? How will you draw that? Basically it has to come to this point, right? So it has to come up to that point, and then I can have my something like that, and then okay, so let me call this as VGA. So what happens at VGA? At VGA, M1 is just coming into saturation, M2 is already in saturation. Okay, so the characteristic from M1 to M2, how do you think your output voltage is going to change? The output voltage is going to drop, right? So it's going to fall. So let me say that it falls. Don't worry too much about how it falls. You can think about it and figure out what's happening. Okay, what happens now? So this is my VGA. Subsequently, what happens? Both devices are in saturation. So this slope of V out to V in, what's going to happen? Should it become gentler or steeper? Steeper, right? Because now you have both in saturation. To just see that, if you assume that both of these transistors actually have flat characteristics, how will that fall off be? It has to be vertical, right? Because if both are flat, right, then there will be only one value of Vg for which both these things will overlap, for which both the currents will overlap. Any small change in that current, and then one of them will go into triode, the other will be in saturation. Correct? So that's why I didn't draw both to be absolutely flat, because it's difficult to convey the message. But once I convey the message, taking the limiting case is very, very straightforward. So you're now going to have something where this gain is going to be quite steep, like that. Okay, then what happens? What's the next thing that you can figure out? If I further increase my VGA, yes, right? So what will happen? M2 will go into triode. So I'm going to draw that here. Where will it look? Which one will that be? So it has to come somewhere here, right? And parallel to that, and then something like this. So this I'll call my VGB. Okay. So after VGB, what happens? So call this VGB. Okay. Now, so I can basically name these things here, and then we'll complete this. Okay. So in this region, what's happening? Which are the which transistors in what? M1 is. So let me not use M1, M2. Let me say P and N. Okay. So PMOS is in this region. What is PMOS in? PMOS is in triode, right? That's a black line, M1. PMOS is in triode. NMOS is in saturation. Okay. In this narrow region, you have PMOS saturation, NMOS saturation. Okay. Now, what do you think will happen? Okay. Now, I think I have not drawn it very nicely. just bear with me. Okay, I need some more space this side. This is VGA, this is VGB. Okay. Okay. Now, so you expect that when you decrease it further, what's going to happen? What do you expect? You expect your PMOS to be in triode and your NMOS to be in, sorry, PMOS to be in saturation and NMOS to be in triode. Okay. But there is one other point that you have to keep in mind, and which is what? When do you think your PMOS will be on? What is the cutoff limit for PMOS? So for your PMOS cutoff, what is the condition? For PMOS cutoff, what is the condition? Your V S D. No, okay, sorry. Your VSG must be, so this is cutoff. So in cutoff, what will happen? VSG must be less than VTP. Okay, this is VSG of the PMOS device. And what is that? VSG is VDD minus VG less than VTP, which means your VG must be less than what? VDD minus VTP. Sorry, greater than. Okay, so there is some region here. If this is VDD, there is some region. Let me call that voltage here as VDD minus VTP. And what happens for voltage is greater than VDD minus VTP? Your PMOS is in cutoff. If PMOS is in cutoff, what's going to happen? Current will be 0. So what is the output voltage? What should be your output voltage? It will be 0, right? Or one way of looking at it is, in that cutoff region you will have a characteristic which is basically here, right? Your M2, right? Sorry, yeah, your M1. This is M1, no? What I am drawing is M1. This red, that one is actually, okay, let me not confuse you by that. Okay, what I am drawing is basically for the N1, for the MMOS. Sorry. So this is the cutoff region, right? This is M1 cutoff. So if M1 is cut off, what is the value of current, or what's the value of even this VD? Your current is 0, so the only possible solution is that. So you're 0. So you're going to be 0 in that region. Okay, and now you can complete this. How do you complete this? From here to here, you're going to have some region like that, and in that region you will have PMOS in saturation, NMOS in triode, and the final region will have what? Which will be in what? So your PMOS is in cutoff, and what about NMOS? Continue to be in triode. Okay. So now these characteristics, do they look like anything that you have already seen? Like your inverter, right? It's like an inverter. So this is basically an inverter characteristic. If now I take the same thing, okay, and say I have this, and let me say that I remove all of this nonsense. Now if I say that my if both the Rp and Rn are infinite, how will this change? How do you think it will change? So it will look something like this, right? I am drawing it very crudely, but you get the idea, right? So this is with Rp comma Rn being infinite. So you will get a higher gain. Okay. So in your digital circuits class, where did you bias or where did you operate your inverter? Right. So for your digital circuits class, I am going to draw things in yellow. So you operated in either that region or this region. If you want to use the same circuit as an amplifier, where will you operate it? In that circuit. Correct. So the same circuit can operate either in a digital logic. You only want the level. You are not interested in any amplification. For an analog amplifier, you want amplification. So the same circuit will work for both. Okay. Now let's do something little different. Okay. Any questions so far? No. Okay. So far we have looked at one particular circuit, but it still looks different from the circuit that all of you have already seen. You have seen the CMOS inverter, right? You have seen the CMOS inverter. And the circuit that we had so far does not look identical to the CMOS inverter. How did the CMOS inverter look? Right, it looked very cute, right? There was nothing much in it. We have all these current mirrors and all of that. That was your CMOS inverter. With this was your input and that was your output. Correct? Actually, this should be total and that also is total. Right? So now let's see how we can go from what we have to this. Right? Alright. So you remember for the circuit that we had so far up here, which device is doing the amplification? Only the PMOS is doing the amplification. What about the NMOS device? Is it doing any amplification? No. It is only providing the load. And how do you see that? If you look at your final incremental circuit, the GM is coming only from the GMP. The bottom transistor is only giving you the RN. Right? Okay. So now let's see if we can get both the PMOS and the NMOS to give you some amplification. So now let me just take this particular incremental circuit. Okay. And let me say I have some thing here. Let me call that as some GM. Let me not say what that is. Alright. GM times VI. This is VI. Alright. And I anticipate two transistors. Let me call that as M1 and M2. Right. So I will have two resistors here. Let me just assume that this is the incremental picture for some particular circuit. Okay. Now let me do some massaging to this and see if you can follow me. Okay. Now I am going to split this up into two. This is sourced, right? Tell me if these two circuits are identical. Okay. Now I have my VI here. I am going to connect that. Right? No change. Okay. I have not done anything actually. Okay. Let me go back to the black. I have this. Let me call that as GM1 times VI, and here let me call that as GM2 times VI. Okay. And let me call this as R1, R2, and let me then go and connect these two and take the output here. Have I actually done anything? What have I done? Nothing, right? This GM, okay, R1 and R2, you see what has happened. There is an R1 here, there is R2 here, both are in parallel. What about R1 and R2 here? They are also in parallel. Okay, there is a GM V1 here, so GM VI here. There is a GM1 VI and a GM2 VI. So this is nothing but taking this current source, splitting it up into two current sources and then putting them here and here. So what is the relationship between GM1, GM2 and GM? Very good. Okay, so GM1 plus GM2 is GM. Okay. Now from this particular circuit that you have downstairs, can you see how to go to this? Take this CMOS amplifier that I have drawn here. What will its incremental circuit look like? Exactly this, right? Does everyone get that? So, right? So, this is the incremental circuit. For the CMOS amplifier. Is that right? Nothing, we have not done anything. We have just taken, we knew that this particular block drawn upstairs, right? We knew that this block gives you gain. And so we just split this up into splitting that gain between two transistors, and then we realize, hey, for this thing we can draw this very simple circuit and it will give you the gain that you want. Okay? The only thing is, how do you bias this, right? I have not told you how to bias it. So we'll look at the biasing in a minute, but before that, let's just look at the large signal characteristics of this particular amplifier. All of you have done it, so I can go through it very quickly. Okay. Again, I am going to draw. What should I draw? On this axis, I am going to draw V in, this axis V out, and remember that these are total quantities. I should have actually written in and out in capital letters, but it's okay. Okay. And as usual, what are the two things that points I should be interested in? VDD here and VDD there. Okay. Now, for reference, let me put the earlier circuit that we had and its characteristic. And then you guys can help me. Okay, think about the characteristics for this for the CMOS circuit. You've all done it earlier, so there's only one small difference between what we have done for the common source amplifier and this one. Can everyone see what I have drawn here? Okay, it's only for reference, it's not really, you already know this, just keeping it here so that we can go over this quickly. Okay, all right. Now, can you help me now? All right. At VDD, at Vn equal to 0, what's going to happen? At Vn equal to 0, what will happen? Think carefully. Vn equal to 0, what about M1, what about M2? M1 will be, okay, look at M2 first. If Vn is 0, what is your VGS? 0, right? So M2 is off. What about M1? M1 will be on, but will it be in saturation or triode? Look carefully and tell me. Right? Just look at this. That's why I drew this here. We already had M1, right? So that is not going to change. So PMOS is your M1, M1 will be in triode. Actually, you can go and you can think about it more clearly later also. But what is the value of V out? Yes. Right? It is different from the previous case. In the previous case, you never reached VDD. In this particular case, you will hit VDD. And till when will you hit VDD? Until M2 turns on. When does M2 turn on? When it's V in. What should I put here? It should be greater than the threshold voltage of the NMOS device. Okay. So until here it's going to be like that. Then okay. Now let me look at the other region when V in is say VDD. What do you think this will have? What is this? What about M1 and M2? M1 will be off. Why? It's the same as what we had in the previous case, right? And M2 will be in triode. Okay, go and look at this. I am going over this a little quickly, faster than I usually do, but it's basically a repetition of what we have already done, right? So I am sure you can go and figure it out. If you still have some difficulty, please get back. We'll discuss it. Okay, this is faster than what I normally do. So in this region again, it's going to be 0. And what do you think this particular value of voltage is going to be? This one? No, it's the same thing we had in the previous case, which is VDD minus VTP. Okay, and in the intermediate region, what's going to happen? Right? So you're going to have a region where again you're going to see both of these. You're going to see a region where both are on. Correct? No, actually, let's do that carefully. In this region, what about the PMOS? PMOS is in triode, right? N is off. In this region, P is in off, N is in triode. Okay. Now, how do you think it will all transition? Okay, maybe I can do this. Maybe I'll draw a central region here, and if you go back, right, to the situation where both RP and RN were infinity, you saw that this characteristic was vertical. So let's assume that RP and RN are infinity. So how will this appear here? Somewhere in the middle you are going to have a region where it's going to be vertical. Okay, and what is the property of that region? Both are in saturation. Very good. You have done this, right, in your digital circuits course. You have actually done this. So there's going to be a region in the middle where it's vertical, and in that region what's going to happen? P will be in saturation, N also will be in saturation. Okay, now you can complete this. How do you think it's going to finish? So it's reasonable to expect this and that. And what about this region now? And what about this region? What about this region? And what about this region? So P is in triode, N is in off, right? So N has to turn on. So what do you think this region will be, and what do you think this region will be? Go think about it. Okay, we'll discuss that tomorrow. All right? Can you think about that? Just tell me what is the nature of the transistors in this region and this region. Just think, it's an interesting problem. Okay, I am going to just do one more small bit and then you can go. That bit is to do with how do you bias this transistor. Okay, so biasing of this transistor of this circuit is very difficult, because your bias should be such that both are here. That's a very, very, very narrow window. If you are out of that window, you won't get any gain. Correct? But at least we'll see in the lab as to how you will effectively do it in practice. But one can try and estimate that. So, let me call that as Vg. Now, it is without any capital, without any small letter for the V, because this is the bias voltage. Okay. What is the constraint? At this value of Vg, what should M1 and M2 be in? Saturation. So, at Vg, okay, M1 comma M2 must be in saturation, and the other constraint is, okay, let me call that as Vg 0 just to make sense. Okay. And what is the other thing that you have? Currents are identical. Can you calculate what is the value of Vg 0 which allows this? How will you do that? What is the current in the NMOS device? Half mu n Cox W by L of the NMOS into Vg 0, right, minus Vt n the whole squared. That is the current in the NMOS device, must be equal to half mu p Cox. Assume that the Cox is the same because they are made on the same IC. So, the thickness of the oxide is the same. W by L of the PMOS into what should come here? VDD minus Vg 0 minus Vtp the whole square. You solve for this, you will get your value of. Okay. So, we will see how exactly, again, you want finally you want a bias circuit that has some feedback so that it is stable and all of that. I am not going into that in this course. We will take up that when we are doing the laboratory course next semester. Okay. The aim of what we have done over the last 2 lectures is to just motivate the fact that if you want very high gain, you cannot live with a simple resistor. You need to have an active load, right, because the active load allows you to get high gain with the same value of VDD. The next point we said was that you can in fact get infinite gain if both the NMOS and the PMOS transistor had absolutely flat characteristics in their saturation. And finally, we said that you can get a very simple looking circuit, which is the CMOS circuit, right, which just has one NMOS and one PMOS transistor, and that is your common digital inverter, right. It is difficult to operate that in as an amplifier because you have to bias it exactly at the transition point, and we will see how to do that in a subsequent course. But I guess this gives you a flavor of what you can do if you have both the NMOS and the PMOS transistors in your circuit. All right. Okay. With that, we will close for today. Thank you.